All right, so in the previous lecture, we started chapter 10, and we introduced the concept of rotation, some rotational variables. Then we took a look at how do we convert between rotational variables and translational variable. Today, we are going to continue with chapter 10. We're going to be looking at something called the moment of inertia. We're going to be looking at rotational kinetic energy. And we're going to be looking at something called torque. Okay. So let me share my screen. Now, we'll start by looking at a video clip of something that probably many of you have seen before or heard of. It's a cartoon, but it still has quite a bit of physics in it. Okay, now it goes into fantasy land, but the first bit at least was what we can actually work with. Okay, now what can we, okay, what principles have we so far discussed in this course that we can apply to this short clip that we watched? Well, there's a whole bunch of bollocks in it, yes, but there are still a bunch, some things in it that are actually quite accurate or useful for us to analyze. So let's consider a few things. Initially, they're both standing, nothing is moving. And then they get their thingamabob, what's it called? B-blade, okay? And they pull something. And somehow, because they pull this thing, the B-blade starts rotating. And we have actually studied this already in this course, only maybe we have not actually made the connection yet. Once this thing starts rotating, where does it get the energy from? It doesn't have an internal motor. It doesn't have electrical energy. The only reason this thing starts rotating is because you are converting your internal energy of your muscles into what is translational kinetic energy. Once you start pulling this, you are changing the momentum from 0 to something when you are pulling on the stick, okay, or on the rope. And that is by conservation of momentum. Since the initial momentum was 0, the final momentum also needs to be 0, which means that because I am changing the momentum by pulling this thing, the B-blade also gets a momentum and the opposite direction to conserve total momentum. This is exactly the same idea like when we spoke about the rocket in outer space. The only reason the rocket moves is because when its momentum is 0 and when it expels gas out the back, okay, through a chemical reaction, it needs to balance that momentum out, so it starts moving forward. Okay, that's the first thing. The second thing, when you are pulling that rope or that plastic thing or whatever they're using to pull it, okay, you are actually going in a straight line. So that's translational kinetic energy. Okay, and that's translational momentum. But the thing they're playing with isn't going in a straight line, it's rotating. Okay, what is this rotation? What is its energy? How do we calculate it? How does it convert from translational to rotational? This is what we're going to be doing in this lecture. When the two opposing thingies actually start hitting each other, okay, during the battle, we can see sparks flying. Why? Well, very high velocities, not very low friction, okay, since that's the whole point of what they're doing. Okay, they want to destroy each other's thingamabob. So not a lot of lubrication there. And the result is when metal grinds on metal, you get friction. And if you have high enough friction, you will generate heat, you might generate sparks. Okay, so it's amazing how much we can learn from a tiny thing, as much as this video clip, which is a cartoon that we watched as a pastime, but which actually can still give us a lot. Towards the end of the battle, one of two things usually happens. The losing party either loses their toy because it breaks, which means we have, again, conservation of momentum via explosion, one too many, or it simply slows down, and then eventually goes, and what happens is it ran out of energy. So it flips over. It lost all of its energy. Okay? So given all that, now the bit after this is just, fiction. When they start shouting at it to do stuff and it does stuff, that is utter fiction. But so far, so good. So we looked at kinetic energy when something was moving, and we said Ke equals half mv squared. And that was very nice. Now the question is, let's try doing this again, but with something that is rotating, and we will keep using K equals half mv squared. I have one tiny problem. Remember in the previous lecture when we spoke that the same rotational velocity will relay to multiple different linear velocities. So if I take this, we said V equals R omega, remember? So I'll take 4 different points. What's going to happen is we get different velocities for each point, since V equals R omega. At each different R, I will get a different velocity. Now, this poses a problem. Which velocity do I take? Since it's dependent on distance, should I take the internal one? Should I take the absolute extreme one? Should I take some point in the middle? Should I take every single point and then integrate over it? What should I do? Now, if I am to speak in an utter, well, average might work if it is, average might work, but it will, again, by definition, it will give you an average thing, right? It will not give you the actual value. So again, you have an issue. Now, what I can do, if I have a lot of time on my hand, is take all the points. Okay, I can take the sum of the kinetic energy of all the points and add them all up. Okay. And I will end up with sum of half MIVI squared. Now, the problem is if I have a big chunk of something, how many points do I take? It will be an infinite number of points. But luckily, we have a relationship between this V and omega. And we said V equals R omega, or omega R. So I'm going to substitute this here in my equation. I end up with half MI omega R squared. I'll expand it a bit. I will bring omega squared out of the sum because it's a constant. okay, I end up with half sum of MIRI squared omega squared. Does this remind you of anything? MIRI. Omega is constant because omega is the rotational velocity. And the rotational velocity of all of them is the same, since they all go through the same 360 degrees in the same time. Okay. MIRI was our center of mass. This was our center of mass. Yes. Turns out MIRI squared is something that we see more and more and more often. Okay. And we give it a name. And that name we give it, well, let's give it a letter first. We give it a letter, capital letter I, with units of kilograms meter squared. And we call it rotational inertia or moment of inertia. Now, can anyone remember when was the last time we spoke about inertia in terms of translational motion, and what was the quantity that had something to do with inertia? No? Okay, Newton's laws, good. And in what way did we describe inertia? We said in Newton's laws that things are lazy. They tend to have something called inertia, and to move them, you need to overcome that inertia, right? And then we introduced something that we said explains this inertia thingy in objects. And we called it mass, right? We said the heavier something is, the more mass it has, the more inertia it has. The less mass it has, the less inertia it has. Correct? Now, the fact that we're calling this rotational inertia should tell you something. Just like we said x theta v omega a alpha, okay, now there's direct relationships between these. There is no direct relationship between this, what I'm about to write, okay, but it's the easiest way for me personally to remember mass and inertia. The moment of inertia, or just in short, inertia, is what we call the closest thing to mass that is possible when doing with rotation. So just like heavier objects with more mass are more difficult to push, objects with a higher I are more difficult to rotate. Okay. Rayan, omega is constant, as we said in the previous lecture, because it doesn't matter where you are on the circle, your omega is always going to be the same. Because any point you choose is going to go a full circle, a full 360 degrees, in exactly the same amount of time. Okay. So we can rewrite k from half mv squared for translational motion to half I omega squared. You will see, as I said, half remains half. The I is like the m, and omega squared is like the v squared. So we have translated yet another equation. So rather than summing all the points, we find what the I is, and then we can just multiply that by omega squared to find the total kinetic energy. Okay. Here's a football that goes from left to right without rotating. Has mass m, velocity v. So the total kinetic energy is half mv squared. So far, so good. Here's a ball that's rotating without going anywhere translationally. It has a moment of inertia I and a rotational velocity omega, and its kinetic energy is half I omega squared. Now, question, if I have a ball that is rotating and moving this way at the same time, what is its total kinetic energy going to be? Okay. So if it's rotating and translating at the same time, it will have two kinetic energies. One would be the translational one, half mv squared. The other one would be the rotational one, half I omega squared. So its total kinetic energy is going to be the sum of the two of them. And we'll come back to that later. If anyone has their microphone on, please mute it, because I'm hearing a bit of an echo. Okay. I'll redraw the exact same diagram. Now the question is, okay, how do I find the moment of inertia of this thing? You cannot have zero because you cannot have negative energy unless you are losing the energy. Yeah, remember, it is half mv squared and half I omega squared. M cannot be negative and I cannot be negative, and the square of a number cannot be negative unless we're using unless you're talking about complex numbers, which we're not doing in this course. أي سرعة ليش ما ثابتة مريم؟ You have two velocities in any rotating body. Okay. You have give me a second. Shush. You have two velocities when you're dealing with a rotating body. Okay. One velocity is omega. Omega is how many degrees does any point here go in an amount of time t. Omega is constant for all points in something that is rotating. Okay, whether I am at this extreme or this extreme or here, it will take me exactly the same amount of time to go one circle. Okay, now you have another velocity, which is the tangential velocity. So a point that is here, how fast is it going translationally? Okay, now this translational energy, this translational velocity is equal to V equals R omega. So by definition, the closer we get, the slower it appears. The further we go, the faster it is. Okay, refer to the ending of our previous lecture, the last few slides, when we discussed this in detail. Okay. Exactly, Aham. No, why would the kinetic energy be 0, Mariam? I don't understand. Your total kinetic energy will be half mv squared plus half I omega squared. How could it be 0? If something is actually moving, it has to have kinetic energy. If its kinetic energy is 0, then it's not moving. So by definition, the fact that it's moving means its kinetic energy is not 0. It cannot be 0. Okay. M is always more than 0. I is always more than 0. Since these two numbers, V and omega, are always squared, you cannot have a negative energy. Okay. You might be thinking of vectors. Okay. That if my V is going in this direction and my omega is somehow going in this direction, then they are in opposite directions, so they would cancel out. But remember, energy is a scalar, not a vector. So it doesn't work that way. The numbers simply add up. Okay.
Doctor.
I'm getting that noise. I don't know what's going on. It's like a static noise, and now it went away. Yeah, someone was saying something.
Doctor, I mean the velocity here depended on the radius and omega, yeah?
Mm-hmm.
And the radius is constant.
Radius is not constant. Radius is different
Why?
for each point. Look at this. This is radius 1 for point 1. Radius 2 for point 2 is different. For point 3 is different. For point 4 is different.
Okay.
Okay.
I think the radius.
Yeah. You are thinking of the full radius. This is constant. I'll call it radius full. Yes. But when we're looking at individual points, they have different radii. Dina, yes, the mass is fixed. You're not losing mass for any case for this. Okay. So how do I calculate I? Well, it's the sum of mi/ri squared, but if I have a continuous solid body, that is difficult again to do a summation over an infinite number of points. Luckily, in mathematics, we have a solution for that, which is integration. Okay, so we take r squared dm. Every tiny amount of mass, we add it up until the total. Okay, now this is very, very generic and very general. You will notice there are no limits here or here. Okay, because this is very, very generic so far. So how do we actually calculate the rotational inertia? We have spoken that we have I, we have rotational inertia for a continuous body given by I equals integral of r squared dm. Okay, but how do we do the actual calculation? Now, in principle, we can always use this equation. Okay, you can always use this equation to find the rotational inertia of something. Now, thing is, not only you as students don't like integration, guess what? Pretty much nobody likes integration. Okay, it's difficult, it's a headache, it's not nice. So there are a set of common shapes for which values have already been calculated. Okay, for common axes, and I'll explain why does it say for common axes in a second. Okay, now these common shapes, we will always know what they are, unless we want something different, then we do a special calculation. For example, if you have a disc, a very thin, not disc, what is this called? Hoop. Okay, like the hoopla. And if you are looking for the moment of inertia about this central axis, it will be mr squared, where m is the total mass and r is the big radius. Okay, and I'm assuming this is very, very, very thin. So it has no thickness. Okay. Why are we saying about a central axis? Remember, I by definition is mi ri squared. And r is measured from the axis of rotation. So if, for example, instead of how do I explain? Oh, here, this might be useful. This is a hoop. I have no idea why I have a balloon on my table, but so be it. Okay, this is a hoop. If I rotate it this way, if I rotate the balloon this way, its axis of rotation is in the middle like this. On the other hand, if I decide to rotate it this way, then its axis of rotation is no longer in the x-axis, it's now in the y-axis. So my r's are going to change. Same thing, but with a thick ring, you end up with half m r1 squared plus r2 squared. And here are some common moments of inertia. Okay, and to answer your next question, yes, these moments of inertia are given in your formula sheet for your exams, so you don't need to remember them. Okay, so you will see, for example, for a cylinder going through the x-axis, central axis, it's half mr squared. If you're going through the y-axis, it's actually quarter mr squared plus 1/12 ml squared, where L is the length of the cylinder. And so on and so forth. أي دائرة؟ B? Because it is thick. Look, it has a finite thickness. It's not very thin. It's thick. So it has a distribution of mass. So you have R1, which is to the inner edge, and then you have R2, which is to the outer edge. Here. Okay. Here, look, here where it is very, very thin, it's just one R, not two R's. Okay, some more. Al-Ayham will come to that in a second. There's actually a nifty way, instead of doing the calculation from scratch, we can take the axis in the center, do something to it, and it will give us what about the edge. Okay. Let's first look at this. The figure below shows three small spheres that rotate about a vertical axis. So the axis is like this, and they rotate. The perpendicular distance between the axis and the center of each sphere is given. Rank the three spheres according to the rotational inertia about the x-axis. About the axis. Greatest first. Okay, a few B's, a few C's. Excellent. So most of you got it correctly. The correct answer is actually C. They all have the same moment of inertia. Why? Well, by definition, I equals sum of mr squared. 36 times 1 squared equals 36. 9 times 2 squared is equal to 36. And 4 times 3 squared equals 36. So the three of these would be equally difficult to spin around. Okay. Coming to the question of Alayham, what if I don't want it around the center, I want it around some other axis? Maybe it's on the side, maybe it's slightly off the center, some axis A, not the center. كيف يا أخي مريض? How do I calculate I now? Well, one option is to go through the integral of r squared dm, where you calculate all your r's with respect to this new axis. That is perfectly fine. But again, most people don't like to do integrations. So let's take a look at it from the top. This is my center of mass, the red one, and I want to rotate it with respect to axis A, which is the blue one. The distance between of them is h. Okay. So now I know what is my moment of inertia with respect to the center of mass. Okay, either I have calculated it, or I found it in a ready-made table like this. I know what is it about the center. So I take that and I add to it the total mass multiplied by the distance squared between where my axis is and where my center of mass is. We call this the parallel axis theorem. Let's take a look. For a disk going through the y-axis, okay, we know it's going to be half mr squared. Yeah, I'm going to do an example. Okay, for a disk, this is a disk is basically what? A very, very thin cylinder, right? So if I take a disk, now I know this is not a disk. Okay, this is a rectangle, but imagine it's a disk. And I want to rotate it like this around the center. Okay. Its moment of inertia given by this table is half mr squared. So we know this. But now I don't want to rotate it. I don't want to hold it around the center and rotate it. I don't want to do this. I want to hold it about the edge and rotate it like this. Okay, I don't want to hold it at the center. I want the rotation to be at this axis. That is fine. We do this calculation this way. We use the parallel axis theorem. We know around the center of mass from the table it's half mr squared. And then I will add to it, as per this, okay, I will add to it my total mass and this distance between the two axes square. And this would be our moment of inertia. Okay. Let's do a sample problem. What is the rotational inertia, ICOM, about an axis through the center of mass, perpendicular to the rod as shown? So I want it this way. If this is my rod, I want my center of my rotation like this. I'll write all of it. Okay. My length between them is L. Each one of them is of mass M. My I is MIRI squared. Now, each one of them is half L away from the center of mass, which means M, and this is R, M, and this is R. Each one of them is half an L away. So I have M half L squared plus M half L squared. And I end up with half ML squared. Now, I'll change the question. Okay, through the center, it's half ml squared. But what is the rotational inertia of the body about an x-axis through the left end of the rod? Okay, so initially it was here, and we know it was half ml squared, right? Yes. But now I want it here. Well, I equals I center of mass plus mh squared. So half ml squared plus half ml squared plus the total mass 2m. Okay, and the total distance between this and this is L over 2. So L over 2 squared. I get half ml squared plus 2m L squared over 4. So half ml squared plus half ml squared, which is simply equal to ml squared. Yes, we found that for the center, it's half ml squared. Then part B of the question wanted the I at the edge. That's why, Mariam. Iham 2m because we have two balls, each one of mass m. So your total mass is 2m. Remember this capital, this capital M is total mass. So it is m plus m. This is 1. This is 2. Let's think about it. Consider two masses. أي مسافة مريم؟
دكتور تو احنا قلنا نستخدم هذا القانون ما لما يعني يكون السنتر ما في الوسط.
لا، ما لما السنتر ما يكون في الوسط. لما نعرف ايش هو الاي مال السنتر ونريد نطلع الاي مال المكان ما في السنتر.
وعقب هذاك يعني القانون العادي متى استخدمه؟
اي قانون عادي؟
اللي هو هذا الاي اللي تساوي الهاف ام السكوير.
خلينا نكتب كل القوانين اللي عندنا. عندنا هذا، عندنا هذا، عندنا قائمة متكاملة، وعندنا هذه الأربعة اللي عندنا حتى الآن. طيب، الأولى نستخدمها when we have a discrete number of particles. You have 10, 20, 30 particles, you can use this one. This we use it when we have a continuous body. People who have already used this for common objects, this is equal to this up for common shapes. Usually given I is for or through center of mass. So if you look at this list, it will give you for a disk through the center of mass. It will not give you through the edge, for example. Usually these tables don't give you. This, you use it to get I for axis not equal to COM if already COMI is known. Okay? So what we did for this question is we know from the table that for COM it's half ml squared. Then I use this rule and added mh squared to find what is it at the edge. Okay? Excellent. Consider two masses, each of size 2m. At the ends of a light rod, now you will notice that we keep saying light rod, or in some other questions we will say massless rod. The reason is because we are using MIRI squared, and if I assume this rod does not have a mass equals 0 or much less than 1, so very tiny mass, okay, I can simply use this mass and ignore the mass of the rod. If the rod was actually heavy, I would have needed to also calculate MIRI squared for the rod. Okay. With the axis of rotation through the center of the rod. The rod is doubled in length, so now instead of having L over 2, we have full L and full L, but the masses are halved, M and M instead of 2M and 2M. What happens to the mass, what happens to the I, to the rotational inertia? So if this is IA and this is IB, what is the relationship between them? So we have almost an equal range of answers between A, B, and C. Actually, no, mostly B's and C's. Let's do the calculation. IA equals sum of MIRI squared. Okay. So 2m L/2 squared plus 2m L/2 squared. So 2m times 2 times L squared over 4. 2, 2, 4. I end up with ml squared. IB will be m times L squared times 2, which is 2 ml squared, which means that IB is more than IA. B is the correct answer. Okay. So it is more difficult to rotate something with half the masses and double the rod length. Let's do one more sample problem. I have a disk of mass 272 kilograms, radius of 38 centimeters, and it's rotating at 14,000 revolutions per minute. Okay. I'm actually using an example which I found quite nice. So this is a real world example, which is why I chose to do it. Okay. Large machine components that undergo prolonged high-speed rotation are first examined for the possibility of failure in a spin test system. In this system, a component is spun up, brought up to high speed, while inside a cylindrical arrangement of lead bricks and containment layer, all within a steel shell that is closed by a lid clamped into place. Okay. Now, this is a test where a solid steel rotor, a solid steel disc, like the ones used in a helicopter, okay, of mass 272 kilograms and radius 38 centimeters. When the sample reached an angular speed, omega, of 14,000 revolutions per minute, there was a dull thump, okay, and something happened and it went through the floor. It broke the floor of the building. Okay. So the question is, okay, how much energy was released in the explosion that it went through the roof? Okay. And then next we'll do this one, which is helicopter energies. Well, let's write down first the information that we know. Mass 272 kilograms, radius 38 centimeters, omega equals 14,000 revolutions per minute. First thing first, let me convert revolutions per minute to the SI standard. So I will multiply it by 2 pi and divide it by 60. So I get radians per second instead of revolutions per minute. I get 1.466 times 10 to the power 3 radians per second. Okay, this is a very, very high rotational system, 14,000 revs per minute. Your car explodes if it reaches 7 or 8. How much energy? Kinetic energy equals half I omega squared. We put in the numbers. What is the I of a disk? We get it as half mr squared from that table. We plug in all the numbers. We get 19.64 kilograms meter squared. Now put everything into this I here, put this omega squared here, and you end up with 2.1 times 10 to the power 7 joules. This was a really, really large explosion. Okay. Now let's take a look at this. Another real-world example. A typical small rescue helicopter, okay, so we're talking a tiny helicopter, has 4 blades. Each blade is 4 meters long and weighs about 50 kilograms, has a mass of 50 kilograms. So total 200 kilograms. The blades can be approximated as thin rods that rotate about one end of an axis perpendicular to their length. So we go through one blade, second blade, third blade, and fourth blade, and the axis of rotation, fourth blade, or like this, and the axis of rotation is perpendicular to all of them like this. Okay, now we already know that all the tables are going to give us this axis of rotation, the center. Nobody's going to give us the axis of rotation at the edge. So we're going to have to do some working outs. The helicopter has a total loaded mass of 1,000 kilograms. Calculate the rotational kinetic energy in the blades when they rotate at 300 RPMs. And then calculate the translational kinetic energy of the helicopter when it flies at 20 meters per second in a straight line, assuming, and compare it with the rotational energy in the blades. So let's take a look. Rotational energy, K equals half I omega squared. 300 RPM multiplied by 2 pi divided by 60, we get 31.4 radians per second. You can immediately tell this is a much, much slower system than the ones we had in the previous example. Yeah, in the previous examples, we had times 10 to the 3 radians per second. Here we have basically just 30 radians per second. The moment of inertia of one blade is that of a thin rod rotated about its end. Okay, so let's go to figure 1020 and see if we have something ready or if we need to use the parallel axis theorem. Thin blade, thin blade. So thin blade is basically, I can take a look at a rod. Solid cylinder, no. Thin rod about axis in the center, no. ml squared over 12 plus mh squared, but they have already done this to us, for us. Thin rod about axis through one end perpendicular to the length. It is ml squared over 3. So I'll just use this directly. Okay. So ml squared over 3, 4. One rod, we have 4 rods. 4, each one has a mass of 50, length 4 meters squared. So length is 4, square that, divided by 3. And we get a moment of inertia of 1,067 kilograms meter squared. Now we substitute half I omega squared, half I comes from here, omega comes from here, and we have 5.26 times 10 to the power 5 joules. Okay, so again, if you want to compare, you're talking 2 orders of magnitudes or 100 times less than the previous question. Okay. Entering the given values into equation for translational kinetic energy, so just half mv squared, half total mass 1,000, v is 20 meters per second, you get 2 times 10 to the power 5. So the amount of kinetic energy you get by translating at 20 meters per second is only about 38% of the amount of the rotational energy in the rotors. Okay, so most of the kinetic energy of the helicopter is in this and is in its spinning blades rather than in its actual movement in a straight line. Okay. We already did this example on parallel axis theorem. Okay, we go to torque. A few slides left. Okay, let's think of a door. Get me the strongest person that you can think of. This is our door. This is the hinge. I'm holding it from here. Now you get a small child and you tell them to open the door. They push it from here and it will open. Easy. No problem. You tell someone to push it through the center, it will still open, but slightly more difficult. Right? But get me the strongest person you know and tell them, open the door, but don't push it from here or from here. Push it from near the hinge, somewhere here. You need an enormous amount of pressure. See, I can't even do it with one finger, even for a calculator. I need 3 fingers or 2 fingers to be able to open it, to rotate it. And there's a reason for that, and that reason is what we call torque. And when we're looking at the door from above now, okay, we want to open it. And we can put the exact same force at it at 3 different places, but we get very, very different results. At this point, the door will be easily opened. Same force this point, more difficultly opened. And same force at this point, very, very difficult to open the door, almost impossible. Why? Well, before we say why, we'll talk about one more thing. You apply that same force in this direction. It doesn't matter how strong you are. You might pull it strong enough to take the entire door out of the wall, but it will not rotate if you pull it just perpendicularly like that, right? The reason is because the distance from your axis of rotation actually matters. Okay, it's not just push it at a random place. There is a reason why pretty much every single door handle you have seen on your life is at the end of a door. Okay, there's also a reason if you watch movies, of banks, for example, a bank heist or something, you will see that very high security doors for panic rooms or for banks or whatever would usually have locks here and here also, not only lock at the end. Okay, because distance from the axis matters. And this is what we call torque. Torque is the quantity that indicates the ability of a force to cause rotation. So it's no longer only about how much force you put, it is how able is that force to cause a rotation or not. You will see that sometimes 10 newtons is enough to cause a rotation. Sometimes 10,000 newtons is not enough to cause a rotation for the same system. Let's take a generalized example of me pushing a door, but instead of perpendicularly, at an angle. Okay, some angle phi. I am pushing at some distance r from the hinge. Now, this dashed line that goes through my direction of the force is what I call the line of action. Okay. Not like a pendulum, not exactly like a pendulum, because in the pendulum, you are going translational motion. Here, you actually have a rotation. Well, in one way, yes. A pendulum is similar because the shorter the pendulum, your time period is different, your force is different. So yes, sort of like a pendulum. Okay. Now, two definitions. Line of action is the line through which the force takes place. Moment arm is the perpendicular distance from that line of action to the hinge. Okay, now these two phi's are similar. Okay. And torque is defined as R cross F. Cross product. This is not just times. This is the cross product from vectors. Remember, A cross B, R cross F. In easy cases, this is the same as RF sine theta or sine phi. And it's given, its units are Newton meters. You have to, when you're at an angle, you resolve into components. You have a perpendicular force, which is F sine theta, and a parallel force, which is F parallel. Okay. F perpendicular actually contributes towards rotation. F parallel does not. Okay. So yes عزان, it is عكس الشغل, مش بالضبط عكس لكن نوعا ما, لأنه in work you are looking for the work in direction of the force. So you're looking for the dot product, which is why you use the cosine. For work, you want the parallel component for work. For torque, you don't want parallel, you want perpendicular. So you use the sine, the cross product. Okay. As usual, counterclockwise is positive, clockwise is negative. Let's take a look at this. We have a door, something, torque is RF sine theta. If I am doing just parallel, what is my theta here? 0. And sine theta is, sine 0 is 0. نور ما فهمت السؤال. Okay, I'll continue until Noor replies. No, force causes torque. Yeah, force causes torque. Torque is not force, force is not torque. You get torque because of force. Okay, so this is torque, and you can see that force causes torque. It's part of the equation. Okay. This is a common misconception. Force is not the same as torque. Torque is not the same as force. Yes, they are related, but they are not the same thing by any means. Okay. What she said. Okay, قوة العزم. I'm assuming. Okay, what if I have a perpendicular force? I will have RF sine theta. My theta is going to be 90, and sine 90 is 1. So it's simply going to be RF, maximum torque. Now, what if I have my same force perpendicular, but at the axis itself? What's it going to be then? My R is going to be 0. So my torque is going to be 0. And that's why it doesn't matter how difficult, how strong you are, opening a door by pushing at its hinges is a moot point. Okay. If you go very close to the edge, okay, you will not get 0, but your R is going to be small. So your torque is going to be small. Let's do a few conceptual issues. Okay. You are using a wrench and trying to loosen a rusty nail. Which of the arrangements shown is most effective in loosening the nut? A, B, C, or D, or they all have the same effect? You will know the struggle if you have ever غيرتوا cylinder غاز في البيت. Okay, you have a whole range of options. Let's take a look. For A, my torque is going to be R cross F. RF sine theta, it's at 90 degrees, so it's simply going to become RF. For B, it's the same thing, but my R is way bigger. Yeah, my R here is way bigger than the R here. In C, I am going to have, it's the same range as this, A and C are the same, so I'm going to have RF sine theta. Theta is not 90, so it's going to be less than A. In D, your rod here, it's at 90 degrees, so it doesn't really provide you with any extra torque, because your torque is still going to be R cross F, which is RF sine theta. Okay, only now your R is either this, if you're holding it from here. So if you're doing it here, you will still simply get RF. And if you're holding it from here, you will get slightly more. Okay, so R plus R square rooted F, but then again, you will have an angle theta. Yeah. So your correct answer is B. And this is, if you have, this is why the next time you have someone change your gas cylinder at home, go take a look and you will see that they are using really large spanners because it makes it much easier to pull. It provides way more torque. An object with a triangular cross section is free to rotate about the axis shown. 4 forces with identical magnitudes are exerted on the object as shown. Which one of the forces, if any, exerts the largest torque on the object? This is the center of rotation. So we know it's not 2 since the R is 0. 1 and 4 would give you the exact same. Actually, this is the distance of 4. This is the distance of 1. Yet this is the distance of 3. And if the F is the same, then torque equals RF sine theta. Bigger R, same theta means 3 is your correct answer. Okay. Revision. Is it possible for a really large force, 10,000 newtons, to produce small or zero torque? Yes or no? Excellent. There are two ways for that to happen. One, the angle is really large, or two, it's really close to the hinge. So either way, you get very small torque. Okay, B, is it possible for a small force to produce a large torque? And the answer is again, yes, but there is only one way for it to happen, and that is, if this is your force, this is your wrench, okay, for example, you will want a really, really long wrench. Actually, this is a bad example. You will need a really long wrench, and the tiny force F here will be amplified because your torque is RF sine theta. So if your R is really large, your torque is going to be large. Okay. This is the end of today's lecture. Let me take a look at these. As a homework, if you have time, I would say try this point, 10.6, check your understanding about the Costa Concordia, which is a recent event that happened. You might have read about it in the news. It's very relative. It's very, very good point, and it's a really good exercise to see if you have understood your torques or not. Okay. That is it for today's presentation. أيوة.